Well, we're ready to perform another experiment in the laboratory, so it's time to look at the consolidation of soils from a theoretical perspective, and then we'll prepare to show an example of the experimentation. This image here, as you can see, is a laboratory in at Vienna Technical University in the mid 1930s that Terzaghi has developed. You can see a number of different experimental setups there: permeability machines, shear boxes, and shear apparatus. But the far left is the one that is of our interest today. That is the consolidation frames, and that is specifically used, it says, for pre-consolidating shear samples. So it's preparing the samples from a consolidation perspective to go into the shear devices and then be sheared. But that is very similar setup to what we're going to be utilizing today, just to look at the consolidation properties of soil. So let's get into some of the aspects of what that really means. And so our learning objective today really is to determine the compressibility properties of soil utilizing the consolidation test. And so that specifically means that we want to determine the compression index, the recompression index, or the swelling index, and the coefficient of consolidation of soils. Those are the parameters or the properties of soil that we want to determine utilizing this experiment. And so let's go ahead and back up a little bit and say, what is settlement? Settlement is a term that we can probably understand from a conceptual perspective of something that is settling or reducing in size. But from a soil mechanics perspective, it really is similar to what we've learned in basic mechanics. It says that when we have an elastic type material, or it doesn't even have to be an elastic material, but most of the time when a stress is produced on some sort of material, that produces a strain. A normal stress produces a normal strain for most elastic materials, and if you integrate those strains over some length, you get a full deformation. And that is valid for soil, although it's not necessarily elastic in nature. It is somewhat elastic for some soils, but not necessarily for all. And so loads that are applied to the soil surface produce changes in stress, in vertical effective stress. Those changes in vertical effective stress produce a change in strain, or produce strains, excuse me, and those strains can be integrated over a distance or a length to give us an overall settlement. And that is the downward movement of soil as stresses or loads are applied at the surface or some location. And so what I like to tell students is it's not a matter of if settlement will occur, it's how much, and can those settlements be confined to tolerable limits that are placed on that site or for that structure. I also add, and we'll see this later, is how much time will it take as well, because that is another aspect that we need to often utilize and understand when we look at calculating settlement. So the word settlement really can be estimated by three different broad categories. We have the first type of settlement, which is an elastic settlement, and that is a standard deformation from a linear or elastic perspective of sands or dry soils. And that is that can be utilized in this experimentation, but it is fairly simple, and oftentimes it's very small. The next one listed is primary consolidation settlement, and that is when we have saturated soil, often clay material in nature, and the saturated material oftentimes does not allow the water to expel or travel through the soil structure very easily, and so it takes some time, and so we really want to understand this property specifically, and that's what we're really going to focus on with this experimentation. There's a secondary consolidation settlement that occurs after the primary consolidation is typically complete, and that is the adjustment of the soil fabric or the structure, the skeleton of the soil properties under constant effective stress. And so ultimately, if we have layers of soil, we would combine all of these together to get the total consolidation for a site. We are going to primarily be focusing on the primary consolidation settlement today in today's experiment. And so consolidation what does that mean? Well, that refers to the compression or settlement of soils due to loading. This loading produces corresponding vertical effective stress, which, as we've already stated, produces strains. Again, this is a time-dependent process because oftentimes the soil has an attraction to the water that does not allow it to expel or travel through the soil very easily, and sometimes it can take a very, very long time for that settlement to occur. And this experiment allows us to determine how long that does take. Why is it time dependent? Well, sandy soils are often allow permeability to occur very quickly. Water drains immediately, which means we do not have a change in pore water pressure that exists between the pore space or the void space that exists between particles as load is applied. That is quite different for cohesive type soils that have this attraction to the water, and so water drains very slowly. And when load is applied and stresses are applied, then the pore water pressure is carrying the load instantaneously or immediately, and then over time, as the water is allowed to expel or dissipate, travel through the soil, though that pore water pressure transfers to an effective stress change within that soil structure itself. Here's an illustration of what we were just talking about. Initially, when a stress is applied, as you can see in the upper left image, we have an initial height of that soil sample, and an initial stress is being applied due to body stresses or the geostatic stresses that exist. When an additional change in stress occurs, then that produces a deformation or a consolidation settlement of that soil sample. And what is really occurring, if we assume, which we must, that Darcy's law is applied, meaning the water and soil are both incompressible, the only change that can occur is an adjustment of the void space that exists between the soil particles. And so as the initial stress is being applied, the void space is being reduced. The volume of the solid material does not change. And so that allows us then, if we look at those properties, we can say, I've got to figure out a way that I can predict the amount of settlement that could occur on a site. If I can acquire a sample from that site, do some sort of experimentation on it, and on how it's going to behave under the loads that we anticipate placing on that soil, we can then predict what that site will do once a structure is being built. So settlement occurs when loads are applied. How much deformation will occur and how long will it take? So now that leads us to this experimentation of one-dimensional consolidation. One dimension meaning that the soil is confined in all axes except one, which is the vertical axis. And that makes sense because we are typically applying stress to the soil surface. And that is then, if it's a large area, that is then assuming that the soil will act from a settlement perspective in the vertical axis. So the procedure is very simple. I'm going to get into this a little more detail when we see some more images, but you obtain an undisturbed soil sample from a job site at various depths. And that soil sample is then installed into what we call an odometer or a consolidometer. Which is the device you see on the upper left there. This is the consolidometer here, this device here that contains the soil. You submerge the soil sample. Typically these samples are underneath the groundwater table, so it needs to be submerged. And you have a porous stone at the top and bottom of the sample to allow water to pass through the soil, but the soil particles to remain intact. And sometimes you will apply filter paper as well, depending on the type of soil. And then once this consolidometer with the soil sample and the porous stones is assembled, then it is placed in what we call a water bath, and that is this device here where it is submerged, and that entire device is placed into a frame. That frame then allows us to apply load to a hanger, and that hanger then that load that's applied to the hanger applies that load to the soil sample itself, and then we begin to record deformation of that soil sample over time. And typically this lasts about 24 hours or until no more deformation occurs. And these are fairly small samples, so typically the deformation is completed within a 24-hour period. And then another load is being applied. Typically you start with a lower load and then you work your way through doubling those loads each time, and you perform a 24-hour reading process on each loading increment as this is being loaded up until a certain amount. Typically you go to the range of the device itself allows, and then you can also unload that sample as well. So removing weight can also, and then recording the rebounding effect of that can also give you some interesting information to allow us to look at how the soil will rebound, or what the effects are of that soil sample when loading is when the soil has already experienced a certain amount of stress. All right, so this image here gives you some a little bit more of an information, but it also builds something called the E log P plot, which is what you see at the bottom of the screen there. This illustration comes from the Caduto, Young and Kitch textbook that we use in class, and I really like it because it allows us to really see what is occurring to a soil specimen in the field, and then also in the laboratory what we can simulate. So on the far left here we can see, and what I usually do is say, okay, soil particle A comes strolling down the ground surface and ends up right there at that location. And then over time, more soil particles begin rolling down and covering up that soil sample. Well, initially, when that soil particle A ends up at the ground surface, there is not a lot of stress that's being applied. It's very low stress or no stress at all because it's at the surface. But also, when that soil is first being developed, there is a very large amount of void space between the soil particles. And so that's indicative of point 1 here, where you have very high void ratio and zero or very little stress that's being applied to that soil sample. But as more soil particles get blown down or flow down, or however this soil is being layered and developed, the geostatic stresses that are being applied to soil A are increased, as you can see here, but also that is reducing the void ratio, and it's changing and reducing the void space between soil particles due to the stresses. So now you see a change from point 1 to point 2 here. As stress increases, void ratio decreases. And then a couple of thousand years later, a company comes in and drills a hole into the ground and extracts soil particle A from the ground. And what happens there is interesting, because the stress is relieved, as you can see here, between points 2 and 3, the stress is reduced. However, the void ratio does not rebound or does not go up the same slope as originally anticipated. The soil then has a new behavior. And that new behavior is what I like to say is soil has a memory. It knows what the largest amount of stress that has ever been felt in its history. It has that memory. And so because the soil particles have been rearranged and changed and moved, the amount of void ratio does not rebound the same as it did in its original structure when it was first fully formed. And so when it's retrieved from the ground, as you can see here, the stress is reduced, but the void ratio is also reduced, but not back to its original state. And then that soil particle A is taken back to a laboratory, placed in a consolidometer, and then more stress is applied. Initially, the stress is applied back to that soil sample to simulate what the geostatic stresses are from when it was extracted in the field. And I want you to notice that it follows the same slope or path from 3 to 2 as it did from 2 to 3. I mean, from 3 to 4 as it did from 2 to 3. It follows a similar pattern. And then all of a sudden, more stress is being applied. So say your first increment of stress was from 3 to 4, okay? And then more stress is being applied from 4 to 5, okay? Well, that being the case, notice that the slope of this ratio of stress to void ratio follows the same curve as it did previously, right here. It does not continue down this path here. This is not correct. And so that being said, this follows a slope that we call the virgin curve. The virgin curve is this slope from 1 to 2 and from 4 to 5. And it has, and this is that slope is indicative of the fact that that soil has never experienced that amount of stress in its stress history. But it has experienced stress between 2 and 3 and between 5 and 6. And notice the slopes between 2 and 3 and 5 and 6 are the same. And that follows what we call the recompression curve. And so that being said, let's go ahead and look at how we can identify the data from this experimentation to represent what we just explained. Now the curve on the far right here shows what we see: a recompression curve, a rebound curve, or what we call a swelling curve, and a virgin curve. And I want you to notice that the rebound curve, or the swelling curve, and the recompression curve have the same slope, but the virgin curve has a different slope. And those are very unique and interesting and very important in understanding how the soil will behave under stress. Okay, and this plot right here that you see, the stress versus the strain or void ratio, includes all loads that have been applied to that soil sample in the laboratory experiment. And this is called the E log P plot. So it is the void ratio versus the log of the stress. Okay, and so that, again, this includes every loading increment on one plot. And that is one piece of information or data set that we need to determine. Now we also need to understand what the deformation compared to the time of that 24-hour period also has, the behavior of the soil over time. And so the curve on the left shows the deformation or the change in height of a sample versus the log of time. And this is, again, or not again, this is explaining each loading increment will have one of these plots. So if you do 10 loading weights on one sample, you will have 10 different plots of these deformation versus time. Whereas all 10 points will be on one plot here for your E log P. Okay, so we need to determine all of these data sets and to allow us to understand the properties of how the soil will behave under stress. And that leads us to what the difference is between those two curves on the E log P plot. Now we have two different types of understanding of consolidation. We have normally consolidated material and we have over consolidated material. And one soil sample can give us information about both of these pieces of data. Normally consolidated soil means that the current stress that exists on that soil is also the maximum amount of stress that that soil has ever experienced. Okay, that means its initial effective stress equals something called a pre-consolidation pressure. All right, over consolidated clay means that the current stress is less than its past maximum, that stress that that soil has ever experienced. The past maximum is now called the pre-consolidation stress or pressure, and we can determine something called an over-consolidation ratio, which basically tells us how much stress it has felt in its past compared to where the stress it's experiencing right now is. The overconsolidation ratio, or OCR, is just a ratio of its pre-consolidation pressure, its past maximum, compared to its current amount of stress. Okay, so let's look at this from a graphical perspective. This might seem a little unusual, but let's look at it from a graphical perspective. We mentioned before that there are two slopes on an E log P plot. And we can see this on the plot to the left. The slope between A and B and the slope between D and C are similar. That slope means that the stress at A to the stress at B, the soil has experienced that amount of stress in its past. Okay, so the stress on this side from here to here, that soil has experienced that amount of stress in its past. Okay, and then once it gets past B, it takes a new slope. This is its new maximum stress. That becomes its virgin curve, and that slope is the slope of the virgin curve. Now again, if it rebounds from C to D, then the slope, the soil has experienced that stress in its past, so the slope will be different. Okay, so ultimately, the bottom line here is that if the soil on this side of that line here is over consolidated, on this side of the line it is normally consolidated. And then when it gets to C, now this part is over consolidated. Again, if you stress it more this way, more stress, it will become normally consolidated again. And so if we look at this plot, we can say that some location right in here is the pre-consolidation pressure or stress that exists for that soil. And a way to determine that is utilizing Casagrand's method. Casagrand's method to determine what the pre-consolidation pressure is of a consolidation plot, or an E log P plot. And this goes through this process. I'm not going to go through it here, but I've shown you this before, and it's in the textbook. So now let's get to an understanding of what information we can gather from this plot. The slope of the recompression curve is called the recompression index, and that is C sub R or C sub S. Really, the recompression index is the slope, the initial slope of the point of the soil that is over consolidated when it's first placed into the soil sample. The swelling index would be like a rebound curve here, but they are typically very similar in slope. And the virgin curve slope is called the compression index, or C sub C. And so if we understand that piece of information from the E log P plot, we can then start to predict what the ultimate settlement will be for soil utilizing primary consolidation. For instance, in this case, we have a medium clay, a meter depth of medium clay that is between a fine dense sand and a dense gravelly sand. And so that clay layer, it's under the groundwater table, which means it's assumed to be saturated. If we perform a consolidation experiment on that clay material, we should get some information regarding if it's been over consolidated or normally consolidated, and what the compression index is and the recompression index is of that soil. And then we can identify or predict the amount of settlement that will occur depending on the amount of stress that's being applied at the surface. And that's what these equations here represent. So I'm not going to go through the derivation of this, but I will say this, that this equation here is the ultimate primary consolidation of a clay sample that is normally consolidated. And the reason I know that is because this uh, coefficient here is the compression index, meaning that the stress state that soil is in right now is the same as its maximum past stress that is ever felt. And as you add more stress to the soil, it will follow the virgin curve line. So the behavior of that soil is dictated by that virgin curve that we experience on the E log P plot. Okay. Now, if we are over consolidated, or the initial stress that we start with from our soil sample is on the left side of the pre-consolidation pressure, then we have two different cases that could exist. The first case could be that when we start off the initial stress and then apply an increase in stress to the soil sample, we still are below the pre-consolidation stress, which is right here. And if that's the case, we utilize the exact same equation, only the behavior of that soil is utilizing the recompression index. If we start with an initial stress on the left side of the pre-consolidation pressure, but then end up on the right side of the pre-consolidation pressure, now we have a two-term equation that must be utilized, because the amount of the behavior of the soil from the initial stress down to the pre-consolidation pressure will follow one behavior. Once it hits its past maximum, it will then begin to follow this behavior. And so we must have two terms of our settlement equation utilized. And so that leads us to now understanding prediction of the ultimate settlement that could occur when a stress is being applied to the soil sample. But now we don't know what will occur over time. That doesn't give us any indication of time. That's the ultimate consolidation. That's just utilizing the E log P plots. So now what we want to do is we want to look at how we can determine the amount of time that it takes for the soil to complete its primary consolidation. And that utilizes an interesting theory that Terzaghi came up with to quantify this process. Okay, so the load that's being applied to a soil increases its vertical stress, and then it is initially carried by the change in pore water pressure, because the soil typically doesn't allow water to escape its grip or its attraction initially. It takes time, and that's why we look at each one of those increments in a 24-hour period. But as that pore water pressure changes, we have localized change in head, which creates a hydraulic gradient. With that hydraulic gradient means that we have a need for the water to travel from high energy to low energy. So as that pore water pressure that was increased due to the load changes, it will reduce. The vertical effective stress begins to increase and settlement occurs. How do we quantify this process? Well, first we have a number of assumptions that must be made. These are all valid and understood, especially if Darcy's law is valid, which we must assume in this case, that the soil is the same all throughout, even though we know it's not. It is saturated, which typically it is. Water and soil grains are both incompressible. And the process is one-dimensional, which we know is not also the case, but it simplifies things enough to where we can go ahead and assume that it gives us good enough results. The next piece to this is to understand the drainage path. And the longest path of a water molecule must travel to escape the confines of the soil becomes very, very critical in this case. If we assume that this is just vertical flow and assume linear in nature, then we must then account for what the longest drainage path or travel distance that occurs for an increased stress to escape the confines of that soil sample. And so if we assume that that the drainage material at the bottom of our clay layer is similar to the top, then we can assume halfway through that soil sample is our what we call our drainage height, H sub dr. If we assume that or if we have an understanding that we have an incompressible soil or a different type of material beneath our clay layer, then that drainage path becomes the entire length of that soil height that we're analyzing. And consolidation time is directly proportional to the square of the drainage height distance. If all things are equal, if you double the thickness of that layer, it will require four times the actual time to consolidate that layer. That becomes very critical when we have to understand how to estimate the amount of time it takes for the consolidation to occur. And this can become very important when we're trying to estimate the construction time consolidation versus the overall consolidation, or if we're trying to preload a site to try and eliminate some of the compressibility effects of that site. And so the rate of the consolidation depends on the amount of pore water pressure that exists, as well as the stress that is occurring between the particles. And all of that put together, Terzaghi came up with a theory that says that one-dimensional consolidation is essentially the partial derivative of the change in pore water pressure to the change in time, compared to the square of the change in pore water pressure to the square of the change in height, which we talked about, the drainage path, multiplied by some constant some constant called the coefficient of consolidation. This can be estimated by this equation here or determined in a laboratory setting. And we're going to determine it in a laboratory setting. That the answer to that second order partial differential equation that we saw looks something like this, but the important feature to this is this T sub v right here. That time factor equation becomes very critical and important for us to utilize to determine what our coefficient of consolidation really is. And as you can see, that time factor just equals this coefficient of consolidation multiplied by the time it takes to consolidate divided by the square of the drainage height. And that is directly related to the percentage of the ultimate consolidation that occurs that we can see from the E log P plot. Okay, and here are some correlations between T sub v and the percentage of consolidation that exists. That takes us to how to determine the coefficient of consolidation. Well, we determine that by looking at the deformation versus the time plots that we saw previously. From those plots, we can determine what C sub v is because it shows us what the deformation is over time. And we typically use the first two, the log of time method and the square root of time method. And I'm going to show you both of those here. The other two are some features that have been added with research over time. So the log of time method is usually utilized in a clay type material that it takes a long time for consolidation to occur. And as you can see, the deformation increase downward over time in a log scale. And so that typically produces a plot that looks like this. And so what we can do is there's a procedure to determine what the T sub 50 is, or this is really the time of 50% consolidation has occurred. And so there's a procedure to this that's based on the initial drop and some changes in height from the initial, which is D100, and then back up to the top, which is D0. Splitting those in half, we get our D50, where that D50 crosses the T50 and then it's placed into the equation. This is your time factor equation, just rearranged to solve for C sub v. Your time factor in this case, 0.197, equates to the 50% consolidation. That's your time factor at U of 50%. And so we can determine C sub v from this plot. We can do the same thing with the square root of time method, which is again your deformation increasing downward. And you get a plot. If you take the square root of time versus that deformation, you get a plot similar to this. And so there is a method again to determine not T50 this time, but T90. And so we go through this process where we have this, which is 115% of an increase, and where that crosses the initial trend gives you a square root of T90. You square that, place it in this equation. Again, this is your T sub V equation, but this time T sub V is for 90% consolidation. And then you determine C sub V from this plot here. And you can do this, and in your experiment, you're going to perform both of these types of analysis on the data. And so now we're going to go to a quick explanation of how to set up the experiment itself. All right, so what we have here is all the pieces to the consolidometer. That the first thing I picked up was the water bath itself. Now what I have in my hand is the cutting ring, and that's the ring at which the soil sample will be placed into to confine it on all sides except for the top and bottom. So you'll need to get an average height of that cutting ring so you know how tall your sample is going to be. And then you also need to get an average diameter of that cutting ring. And typically this one here is about 2.5 inches diameter and about 3/4 of an inch tall. It's probably a little bit more than that. It's probably about 0.77 inches tall. But get the measurements in about 3 locations. Take an average, and then you want to get an empty weight of that cutting ring too, because you need to know what the actual weight of your sample is so you can determine what your density is. Next, we'll get a soil sample. We are lucky enough to have some great companies locally to provide us with some great samples. This is a silty clay sample that was given to me for this experiment. We have a wire saw that we can cut a portion of this sample off to utilize for testing. We need to have it at least a little bit thicker than what that cutting ring is, so we can trim both the top and bottom and fill up the entire volume of that cutting ring appropriately with the soil that we need. And that's what I'm doing here now using a wire saw. And this is an undisturbed sample from a Shelby tube, and we're going to try and minimally try not to disturb it as much as possible. Be very minimal with the amount of disturbance of that sample itself. And so we want to restore the rest of that sample too, and hopefully when you're in the laboratory you can get another portion of that sample. The lid here gives a lot of information as far as the job number, the boring hole number. That is sample 4 of the Shelby tube, and that is the depth at which that was collected. I think this one's about 120 feet below the ground surface. And so that information is very important and relevant to understanding what sort of stresses should be applied to the soil sample during this experiment. Now that we have our sample that's trimmed or minimally trimmed to appropriate size, then we use the cutting ring to cut through and install that sample within that cutting ring itself. Sometimes this takes a little bit of force to do. Sometimes you have to trim it into place, and you want to do this with at least amount of disturbance to that sample as possible. Notice that the sample itself is about 2.8 or 3 inches diameter, but the cutting ring is 2.5. That's intentional. We can take some of the excess material from the outside, and we are going to collect this material and get a moisture content of the soil sample as it sits before we begin the experiment. So not only am I trimming that away from the cutting ring, but I'm going to collect some of it in a tin so we can get a wet weight, put it in the oven, and get a dry weight. We call this the before experiment moisture content. And so once we have that completely embedded, we trim the top and bottom and get a weight of the soil sample in the cutting ring itself. So we know how much the soil sample is because we got the weight of the cutting ring. Then we get obviously the wet weight and of our sample and put it in the oven for drying overnight. Now we have that's a water bath here, and that water bath is pretty unique. You might have one similar to this or it might be a little bit different, but there are 2 porous stones, one at the bottom and one at the top. And we need to make sure that those porous stones are saturated, because the point is we want to make sure that this soil sample is saturated completely. And so it just helps to make sure that we get water in the top and the bottom porous stone there. I did the bottom part. Now we're going to do the top porous stone as well, just to make sure that because that stone has a lot of pore space in it, and we want it to be filled with water and not air. So sometimes it might take a little bit to get through, but we'll go ahead and place that into the water bath. You want the rough side against the sample itself. Then place your soil sample in with the thinnest part of the cutting ring at the top. That is your loading, or that's the frame that keeps that cutting ring in place, and that will slip over that smallest piece of that cutting ring. Force that down, and then there are 3 knurled nuts that go on the top of that to keep that in place, and that allows that cutting ring to remain in place while the soil sample is being consolidated, as you can see here. Once those knurled nuts are completely installed, and you want to do this just hand tight is fine. This is a brass unit, so it's a very soft metal, so you don't want to cross thread those, so be very careful of that too. And then once that is in place, just hand tighten, put the top pour stone in place. Notice there's a flat piece and then a nipple at the top. You want the flat against the soil sample, because the nipple piece there is the location of the top cap, which is right there, that fits into that pour stone, so everything is aligned properly. This is the consolidation apparatus itself that applies the load. It has a counterweight there that I'm pointing to. That's the platform the soil sample will sit in, and notice that the distance there is appropriate for a 10-to-1 ratio, meaning whatever load is placed on the lever is 10 times the amount of weight that the soil will feel. And I'm calibrating that to make sure that counterweight is in the appropriate location. So whatever load we place on that hanger is indeed the amount of pressure that is felt by the soil sample itself, and that can be adjusted by how I'm doing that there. Okay, and most of these should be pretty close. Notice there are 3 holes where that hanger can be located. The closest one is 9-to-1. That's a 10-to-1 and 11-to-1 ratio for a 2.5 inch diameter sample. Once we have that all calibrated, then there's another nipple on the platform. That bottom of that water bath fits in properly right there to center everything. I have a small weight. That's a very small tin with not a lot of weight on it, just to keep everything in place while we put the initial water to saturate the soil sample. So you'll see we need to adjust that crosshead appropriately. Notice it's resting on a loading jack, which I just screwed up, and I'm going to thread that cross beam down into the concave piece of the top cap to where it fits in nice and snug, but it doesn't put any weight on the soil sample itself that's not measured. We put that down in place perfectly into that concave piece, and then we tighten that nut there to put everything in place just where everything is aligned, but no weight is actually on the sample itself. Then we adjust the dial gauge. This is a digital gauge, about 3/4 of the way indented. Okay, because remember, this soil sample is going to be consolidated. The weight is going to reduce that height, and so we want the majority of that to be consolidated, but we do want to allow some room for swelling if possible. Once we get that into place, we zero the digital gauge, and we want positive to be in a downward motion, so negative to be upward in this case, positive downward, as I'm pointing 3 times. All right, so then what we have here is we have placed water into the water bath. We placed that small sample and we let it sit overnight for 24 hours to allow the soil sample to soak up that water. And that image that you saw on the digital gauge was negative 0.54 inches or meters, whichever one you choose. This one was inches. I know this one was millimeters, I'm sorry. And now what we want to do is we want to hold down the load onto the loading jack to where whatever load we place onto that is not felt by the sample quite yet. And so I'm holding it down with my left hand and placing the load that I want to be. This is our first increment of load. and then I look at the time, and then I release the loading jack, so that load that's on the hanger is put onto the sample now. Remember, that load is 10 times what that soil sample feels. And I indicate what the time is and what the initial reading was. It should be 0. I reset the digital gauge every time back to 0, and then I start taking readings, and I take readings 15 seconds, 30 seconds, 1 minute, 2 minute, 4 minute, 8 minute, 15 minute, half hour, 1 hour, 2 hour, 4 hour, 8 hour, and a 24-hour reading. And then I add another increment of load all over again and again and again. Now, what I'm doing here is this is the final one. So I've completed all of the increments of loading. So I'm taking the soil sample now out of the water bath. Okay, but I want to be clear that you need to make sure that you do all of the loading increments the same way, where you lift up the loading jack to just touch it, to reset the digital gauge, and then start the time over again with the new load that's being placed. And you do this for every increment that's necessary. And I'm just showing you the procedure to remove the soil sample from the water bath after all of the tests are completed. All of the loading increments are done. And remember, each loading increment gets a 24-hour reading. Okay, so and you want to take the time measurements accordingly. So now what I'm doing is I'm taking this apart. I've got my soil sample here. You can see that the sample is much smaller in height, obviously because of the load that was placed on it. And now what I would do is I take that porous stone and I push out that soil sample that has now been saturated over a long period of time. And I push that out of the loading ring so we can get it into a dish. And so we can get the moisture content of the sample afterwards. Remember, we got the trimmings from the soil sample before the test began, and now we want to get the moisture content of the soil sample after the test is over. So place that into a dish with just the sample itself, no porous stones or anything else. Weigh it, get a wet weight, put it into the oven, and get a dry weight 24 hours later. And that's the complete test.